everybody, hi, Mike here, and we're ready to continue our journey in the discussion of Lewis structures. You know, it must feel good for you, I hope, to be able to explain why certain formulas are what, like H2O and CH2O is what we're going to do next. And it's not a magic trick, there's rules to it. So before we talk about new concepts, let's do a little more practice, okay? And I'm gonna go quick, all right? So if you get lost anywhere, you might want to go back and rewatch part 2. All right, so we're going to follow the rules for making the Lewis structure of, this is formaldehyde, all right? First of all, who goes in the middle? We need to look up electronegativities, 2.5. I'm not going to bother with hydrogen. Hydrogen never is the central atom. Oxygen's 3.5. So carbon is the central atom in this structure. Next step, let's add up some valence electrons. So carbon, sometimes I like to remind myself so I don't accidentally write 6. I go and I put the Lewis electron dot symbol there to help me remember. So 4 electrons contributed by carbon, 6 due to the oxygen, hydrogen, 2 of those is 2, so we are playing with a total of 12 valence electrons. And then the next step is to distribute them in some way. But first, we've got to make the minimum number of bonds that we can. So I'm going to make a bond between carbon and hydrogen, oxygen, lay them out in space, all right? And we're going to need to make at least 3 bonds to hold the things together. That's going to require 2 times 3 is 6 electrons. So the remaining electrons available are 6. And so let's see if we can distribute them. Hydrogen is perfectly satisfying the octet rule because it only needs 2, which is 1 bond. This carbon has 6 electrons, needs 8, so it needs 2 more, so we need 2 here, and then we need 6 here. So we need 8, but we have 6, and now we got to revisit the bonding step, and so we got to make 1 more bond because we're 2 electrons short. Where is that double bond going to go? I'll let you think for a while. Yeah, you figured it out, didn't you? Can't go between the hydrogens, they can only bond once. That next double bond's got to go there. I'm going to take 2 electrons away. So I can see if I now can revisit that rule, that test where we see if we can place those 4 electrons in a place to give everything a filled shell. So hydrogen, as we talked about, is okay. Carbon, 2, 4, 6, 8 has 8. Oxygen, 2, 4 has 4, needs 8. Oxygen needs 4. We can place those 4 electrons right there. Game over. That is the Lewis structure of formaldehyde. Now, unfortunately, we're going to talk about stuff that happens that doesn't quite adhere to the octet rule next. Okay, so the octet rule is not perfect. It doesn't really accommodate things that are very heavy or light in the periodic table. But one thing we can say for sure is that if the octet rule is going to be violated, it's always the central atom that is the culprit, that nasty, nasty culprit. So a good example would be like beryllium. And actually boron we'll talk about next too. So for example, there's a compound, beryllium dihydride. And I guess the way I can explain this, folks, is that these elements, kind of like hydrogen, are too far away from having 8 electrons. And so what they must do is just kind of find their own way without the octet rule. So if we went and took all the, beryllium has 2 valence electrons. Oops, I put the electrons, so that is goofy. I didn't do that on purpose at all. 2H 2. So you only got like 4 valence electrons between these 3 atoms. And you know what happens? Beryllium just says, I ain't doing that. I can't get to 8. And that is the Lewis structure. So look, I don't want you to really get all upset about things that are exceptions, all right? Boron, it does the same sort of thing. But you know, in textbooks, they'll put this in there in the homework because sometimes the people who write textbook homework problems are, you know, I don't want to say what they are. They're not nice though. So that one will settle for just having 6 electrons, and those are actual things that exist. Let's talk about one where there's too many electrons right now. Okay, here's a weird one. The only thing you need to remember is that the central atom is going to violate the octet rule. This is a real compound. Let's go and see who goes in the middle. It's going to be chlorine, because chlorine has an electronegativity of 3.0, and fluorine, the king of electronegativity, has a electronegativity value of 4.0. Add up the valence electrons. It's looking good so far, because 7 electrons with the chlorine and 3 due to the fluorines is 21, 28 valence electrons. All right, good. Even number, by the way. If you get an odd number, something's really weird. So that's good. That's workable. Now we're going to lay these out in space. Chlorine in the middle. And then we're going to put the fluorines around it. And we're going to make the minimum number of bonds, which would be 6 electrons worth, 3 bonds. Now this is different. Yeah, that's different, all right. I got 2 electrons when I subtracted 6 from 28. That's okay. I did have pneumonia when I was in elementary school, and I missed some of the math lessons. So I'm going to try to distribute those 22 electrons. Fluorine needs 6. That fluorine needs 6. That fluorine needs 6. We've just distributed 18 of them. Now the thing is, that chlorine only needs 2, but we got, after what we've just done, 4. So where do they go? Central atom is going to be the cheater, pumpkin eater of the whole molecule. And what happens is that's something that's allowable. Now don't worry about this too much, but when central atoms get heavy enough, meaning far down enough in the periodic table, they can tap into their d orbitals and hold more electrons than predictable. And that happens. You get weird things where xenon will actually be a central atom of a molecule even though it's a noble gas and already obeys the octet rule. So when stuff gets weird, now look, this is a very obscure molecule, probably hasn't touched your life in any way, but in theory that's what can happen. You can get some very strange molecules that occur and the octet rule is violated. I'd say it's less than 5% of the time you see anything though. So don't worry about it a lot, but just know that that's a thing. Okay, let's talk about something else. Our last item here, we're going to talk about polyatomic ions. Okay, polyatomic ions, these molecules that are ions. Now, if you're in one of my courses, I always just say, hey, let's worry about this later. It's almost like it's a magic trick or something. Now you're old enough to know the truth. I can give you the birds and the bees about the polyatomic ions, okay? Now, when nitrogen and oxygen love each other very much, no, I'm just kidding. Okay, so what happens is, we're going to go ahead and follow the same rules. Nitrogen is a 3.0. Oxygen is a 3.5. Nitrogen's going to go in the middle. And we're going to add up valence electrons. I'm too lazy I'm getting too tired to write the dots now, guys. So we are playing with what? 23 electrons. That's an odd number. How are we gonna distribute those electrons when everything's in twos? Well, guess what? That negative charge is an extra electron that this big blob of atoms has acquired. So what we have is an extra step with these things. We have to take into account the charge. So -1 is 1 electron. Now we're going to try another one of these next time, but if it was a -2, it would be 2 electrons. -3, 3. If it was a +1, what do you think that would be? Time's up. You'd have to subtract an electron. So we're going to go and we're going to take all these and add it up. 24 electrons. Now we're going to distribute 24 electrons to make every atom obey the octet rule. All right. So I got to make 1, 2, 3, 6 electrons worth of bonds minimum. That's going to leave us with 18. So now let's do the test and let's ask each atom, what does it want? Oxygen, what do you want? 6 electrons. Sorry. So then each wants 6 electrons. What about nitrogen? Wants 2 electrons. We need 20. Only got 18. We need to make one more bond. Where's it go? Anywhere for now. I'll tell you the truth about that, but you're not old enough to know that one. That's the one I got to keep away for now. This is now -2 electrons, 16 electrons, and that's going to work out, folks. All right, so what we're going to do is we're going to put 4 electrons there, and then we're going to put 6 there, that's 10. We're going to put 6 there, there's our 16. Nitrogen has 8, and so we've solved the puzzle. So remember, this step right here is very important. Then what we do, or for now we do, we're going to talk about where that -1 resides, if in fact in one place. So that's called formal charge, and that's coming next time. So we'll talk about it then. But for now, we can just put brackets around it. Very acceptable to put brackets around it. And just say, hey, it's a -1. It's just like anything -1, like a chloride or a fluoride. And it's a very prevalent thing. If you're a gardener, you know, or a farmer, this is fertilizer, you know, nitrates. So, good job. We're going to talk about formal charge and resonance structures and maybe something else next time. But right now, you know how to do every Lewis structure there is. Okay. Peace out. Bye.